For a minute, let's forget about chatbots. We're about to dive into an AI that isn't designed to talk, it's designed to discover. This is a true AI research assistant, and it's already starting to change the fundamental pace of science itself.
And really, this is the question at the very heart of what we're talking about today. What if an AI could take on the most grinding, time-sucking part of a scientist's job, which is writing custom code, and not just do it faster, but actually get better results than the human experts who practically wrote the book on it?
So to really get why this is such a huge deal, we first need to pull back the curtain on this giant, often invisible roadblock in a ton of modern science.
Okay, so here's the thing. Many of today's biggest scientific questions, I'm talking from mapping the brain to tracking a pandemic, they can only be answered with custom software. The problem? Writing that software is slow, painstaking work. It's a massive bottleneck that really limits how many new ideas a researcher can even hope to test.
The specific kind of code we're talking about here has a name: empirical software. But think of it like this. It's basically code written to solve a puzzle where you can keep score. Like a weather model that's trying to get the most accurate forecast, or a program trying to predict how proteins will fold. The higher the score, the better your science is. It's that simple.
So, if the big bottleneck is slow, human-written code, what if you could just take the human out of the loop? What if you could actually automate the creation of that high-scoring software with an AI research assistant?
Well, this is exactly what a team at Google went and built. It's an AI system designed to do one thing and one thing only: automatically write and refine code to get the highest possible score on any given scientific problem. It can just tirelessly explore possibilities that a human researcher, they just wouldn't have the time for.
Okay, so how does this thing actually work? Let's take a quick peek under the hood because it's a really brilliant partnership between two different AI concepts.
First up, you've got a large language model, an LLM. You can think of this as the creative partner in the duo. It's the idea generator. It literally reads scientific papers and developer notes, and then it intelligently rewrites the code, trying out all these new strategies to boost that all-important quality score.
But, creativity needs some direction. And that's where the second part comes in: tree search. This is the systematic explorer. It takes all the code ideas coming from the LLM and it organizes them into this huge decision tree, strategically deciding which paths look promising and, just as importantly, which ones are dead ends.
So here's how they work together in this incredibly powerful loop. The LLM is the engine, always generating new code. That code gets instantly run and scored for quality. And then the tree search acts like the navigator, analyzing the result and telling the LLM where to aim its creativity next. It's just this relentless cycle of generate, test, improve over and over.
Okay, so the theory sounds great, but does it actually work in the real world? Let's get to the main event and see how this system actually did when it was pitted against top human experts on some really tough scientific challenges. First up, a massive challenge in genomics. To analyze data from literally millions of individual cells, scientists need software to correct for tiny variations between different lab samples. This is a notoriously difficult problem. So difficult, in fact, that humans have already developed almost 300 different tools trying to solve it. So, how'd the AI do? It didn't just find one better solution. It discovered, get this, 40 entirely new methods that outperformed the top human-developed tools on a public leaderboard. And some of its best solutions worked by cleverly combining existing human ideas, but in ways no one had thought of before.
Next, the system took on a really high-stakes challenge in public health, predicting COVID-19 hospitalizations. The goal here was to outperform the official CDC model, which is considered the gold standard because it actually combines forecasts from dozens of different expert teams.
And the result? It was just incredibly clear. In forecasting, a lower error score means a more accurate prediction, and the AI's model consistently got a lower error score than the official CDC aggregate. It wasn't just a little bit better, it was simply more accurate, period.
And the system proved its versatility again, this time in geospatial analysis. It was tasked with a really critical job for things like monitoring deforestation or disaster recovery, labeling every single pixel in these complex satellite images with perfect accuracy.
And you guessed it, it set a new record. Its top solution hit a score of 0.82, which outperformed other state-of-the-art methods that had only just been published in academic papers. So it wasn't just beating old tech, it was beating the very latest human-developed methods.
The winning streak just kept going, right into neuroscience. The AI built a model that could predict activity across 70,000 neurons in a zebrafish brain. And yeah, it outperformed every single existing method. Incredibly, it even beat these really complex models that took orders of magnitude more time and data to train.
So when you step back and look at all of this, what does it all add up to? Well, these results aren't just small improvements. They're pointing toward a pretty fundamental shift in how science itself might be done from now on.
This quote from the research paper itself really says it all. For any scientific problem where you can define a score for what good looks like, progress is about to get dramatically faster. We are talking about compressing the whole cycle of trial and error, from months or even years, down to a matter of hours.
And that leaves us with this one fascinating final thought. When you have an AI research assistant that can tirelessly and creatively search for solutions at a scale humans never could, which of science's great unsolved mysteries will be the next one to fall?